Yes. Let's start. Thank you. So I was asked by the organizers to chair this session, and I gladly accepted. This talk is by Sachin Sharma, who will speak about representations of map-extended Witt algebras. Please.
Audio is clear?
Yes. Yeah, we see the slides.
Shall I start?
Yes, please do.
Yeah. Okay, so I would like to thank Professor Ivan for giving me this nice opportunity to speak on my work. This is the title. It's related to the representations of map extended with algebra. It is joint with Eswara Rao, Priyanshu Chakraborty, and my student. So later, it's just an overview of talk. And then generalization of Virasoro algebra is nothing but Witt algebra. The proof. Okay. So for what is the Lie algebra? So Lie algebra basically comes from Lie groups. It's just nothing but a set of all left invariant vector fields of a Lie group, which forms nice bracket operations and eventually end up in giving a lot of information, meaningful information about the ambient object, which is the Lie group. So it has a bracket map from G cross G to G, which satisfies these displayed operations. It's a bilinear. The cell, its commutator of any object itself is 0, and the it's a finite dimensional. More precisely, our talk is dependent on related to the infinite dimensional algebra, but it's better to start with the finite dimensional ones. So some preliminary. So you call a subalgebra if it is in its own right. It's again a Lie algebra. It should be a subspace and should satisfies the bracket operation. Should take brackets of each of its elements into inside. An ideal of a Lie algebra is it's an first of all it should be a subspace and the commutator ideal is commutator is non-zero to avoid the trivial case of abelian thing. These are our simple Lie. The nilpotent Lie algebra is nothing but the one who has some nice properties like it's what is called as a central series, which is defined in as displayed in the slide, is terminates at some point. So any like if you take n cross n strictly upper triangular matrices, these are the example of nilpotent algebras. A pivotal role in its representation theory called as the Cartan subalgebra. So what it is a nilpotent subalgebra and it is a self-normalizing one. Means that so whatever the elements which puts an element of H inside H, they are indeed in H. You can always have analog of group theory if you are more comfortable with it. And more, what is a representation? Satisfies the bracket operations. So note that. So it preserves the bracket operation. That's what is nothing but your representation is. It's so one of the fundamental problems in mathematics and representation theory is that to classify representations of the Lie algebras. Okay, so classify all the models given some nice conditions. Another important object is which one cannot simply ignore is the universal enveloping algebra, which is nothing but a quotient of tensor algebra by two-sided ideal generated by this relation. You have bracket operation is nothing but x tensor y plus y tensor x. So these are, if one is familiar with like group thing, it's nothing but an analog of group algebra. Okay. For example, for SL2, it is just nothing but an algebra generated by the element which satisfies this relation of the. So yeah, so for any questions, or if I'm going too fast, one can simply. So let us now we will begin with the notations. So we will always work with the base field C. And for any Lie algebra G, H would always denote its Cartan subalgebra. As mentioned, UG would be its inverse in algebras. B would be a finite generated commutative associative algebra over C. We'll always take an algebra which has unity. G bracket B will always denote G tensor B, usually called as a map algebra, and fundamental to our result. AN is Laurent polynomial ring, where this is a Laurent polynomial ring, and Cn and Zn elements of Cn and Zn are written in the bold phrases to avoid any ambiguity. Okay. And for M belongs to M and these M for a tuple in Zn, we would write T raised to M with nothing but T1 M1, Tn Mn for M belongs to Zn, and Di would be a Ti Dti. It's actually differentials. Okay. I mean, the vector fields. Okay. Okay, so we have notation in our hand. So let us begin slowly towards our problem and what we would want to do. Okay. As mentioned, actually, we are really interested in classifying some of the representations. Okay. So what's the representation? See, arbitrary classification of representation would be a very hard. So let us begin with what is a weight module. So you would like to have your representation with nice property. What I mean by nice property? The nice property you mean is your representation should be behave nicely, as it should be decomposed into the simultaneous weight spaces, V lambdas. These are V lambdas such that each your H of V act, there will be some lambda for all H that will work. Okay. So these are the simultaneous eigenspaces. And support of V, these we are interested only in those. What are those? For which V lambda are non-zero. So elements of support of V are called as weights, and subspace V lambda are called as weight spaces. A G module V is said to be a Harish-Chandra module if all of its weight spaces are finite dimensional. And these are our prime object of studies. So you just studying arbitrary modules is take the situation out of hand, and it will be a wild problem. So people, usually mathematicians, restrict their attention to solve, classify an Harish-Chandra model. And so one of the special class of Harish-Chandra module is a uniformly bounded module. What are those? Those are the for which their weight spaces are uniformly bounded. It means there exists one number n large enough such that it will bound weight specificity of all the weight spaces of V. So of course it comes in a Harish-Chandra module. But not all uniformly weight bounded modules, not all Harish-Chandra modules are uniformly bounded. Of course, the weight can go up increasing. It will never be infinity, but could tends to infinity. So, for a Lie algebra G, and B is a finitely generated commutative associative algebra G, one studies this called as a so-called as a map algebra. Okay. So it's just related to the set of all maps from G to B, and from these functions you can actually kind of have isomorphism, and these elements are nothing but G tensor B, and they are very nicely, they just nice operation of them as a Lie algebra. The X tensor A, Y tensor B is just nothing but it's bracket of X, Y tensor A, B. This makes sense as your B is an algebra. Okay. So this algebra is not it's arbitrary that it's studied. It has great importance. For example, for B is equal to CT and G is finite dimensional simple algebra, it was deeply studied by Chari and Pestri in 2001, where the birth of while modules actually came from their work in 2001, which is a seminal paper which came in representation theory. And the classification of the finite dimensional irreducible representation of G tensor N was done by Rao in 2004, where A in N is Laurent polynomial ring. Okay. And then later this work was extended by Michael in 2015, where he classified all the finite dimensional representation of G tensor B. Here B is any finitely generated commutative associative algebras. Okay. So it has its own importance. And so let us, what are the representation when you consider G tensor B? So note that the famous Cat-D algebras are nothing but the G tensor CTT inverse, consider it as a Lie algebra. And it has a non-trivial central extension. And when you add a degree derivation, it would be nothing but affine Cat-D algebras. Okay, it's just a simply less affine Cat-D algebra, more precisely. And it has been studied as its importance related to the mathematics and mathematical physics. And the theory is very adjacent and actually kind of runs parallel to the finite dimensional simple Lie algebra. And so most natural representations occur as for a G tensor B are a single point generalized evaluation models. What are those? Those which factors through the G tensor B mod MK, where M is a maximal ID. To understand they are very easy. So just take a case K equal to 1. It is called as a single point evaluation module. For example, if you take B, an irreducible G module, and B is a CT. Take your Lie algebra homomorphism, which kind of evaluate T at 1. And you just define for an irreducible module, X tensor Ft of V is equal to phi of Ftxv. Okay. And so you would see that your M is T minus 1 and G tensor M at trivial M. So this is actually an example of a single point evaluation module. When your module is a power, when you factor through the power of some maximal ideal, it will be called as a single point generalized evaluation. Fine. So these would appear. So it's important to mention here. Okay, so let's begin with the very classical algebra, Virasoro algebra, and its representation. To just kind of get the history along itself. So first of all, Witt algebra. So what is Witt? Geometrically speaking, it's nothing but These are all polynomial functions from circle to the circle. These are all tensor. These are all vector fields, and these are f. These are all has form of f d by ft d by dt, where f is function, polynomial function from S1 to R. Okay, so you can simply write down in terms of their basis. These are these Tm1, D1, where D1 is nothing but again Ti, d by dti. Okay, so you have a very nice bracket operation, therefore satisfied. There's this split. Okay, so this is, but interestingly, it has a non-trivial central extension. Okay, and that's what it's called as Virasoro algebra. It is extremely studied object as its relevance to the mathematical physics and its application there. And so, what I mean by it's a non-trivial object, if you take two object, actually two bracket operation, this nice cycle comes here, and this is this makes the theory more interesting. And due to its relevance to the mathematical physics, many mathematicians studied this representation theory of this algebra. And to study actually the representation theory of the algebra, what is the standard technique? You just grade it, first of all, grade the Lie algebra. So it's a naturally a Z-graded Lie algebra with these their graded spaces. V0 is nothing but T0, D1, C, and these are all M-graded spaces. Okay, and you have a natural triangular decomposition, so-called as a natural triangular decomposition of Witt. Okay, in terms of the positive, negative, and zero things. Okay, and that kind of initiate you to define its the highest weight module, analog of highest weight module. What are those highest weight modules? Those which kills the positive part kills it, and repeated actions of the V element would give you your whole V. So that's called as highest weight module. Okay, and so these are the one of the modules which don't come in the category of uniformly bounded module. These are the Harish-Chandra module for especially these things, but they are not uniformly bounded modules. Okay, so let me define the class of uniformly bounded module for Vir. For alpha and beta, and the parameters, the complex constant, you define V alpha beta as a sum of these infinite vectors, and you define action of your Virasoro algebra precisely by the displayed equations. Okay, so alpha and beta relevance is here in the equation, and you shift nth degree will be shifted by Vk to Vk plus n. And more precisely, note that the center will act trivially. Okay, so that is the thing. So Keck in 1982 studied these representations, and Keck and Reina has appeared in 1987. So they kind of formalized an equivalence class of isomorphic modules, those things. So you will see that the translate of Z translates of alpha to V alpha beta is nothing but they are isomorphic. So you concentrate. So V alpha beta is generically irreducible, or almost all the time it is irreducible. So if you kind of if your alpha is not in Z or beta is there, doesn't belong to Z, as their equivalence to the as this they are isomorphic through the Z translates. So one concentrate on V00 and V01, and they also studied and they made comment about that V00 has a unique trivial proper submodule, and its quotient is this, and V01 has a unique non-zero proper submodule. Those things. Okay, and V dash alpha 0 is isomorphic to the V dash alpha. Fine. Okay, so you have an highest weight module now, and these are uniformly where these intermediate module. Are there any module for Vir algebra? After many things of like tackling these things, finally it prompted to conjecture a Keck that for any irreducible Harish-Chandra module over Virasoro algebra, these are the only modules. Either you take highest weight modules or lowest weight modules, or a module of intermediate series. This was a conjecture by Keck. 10 years later, Oliver Matthew, proved in a very nice short paper, proved that, and it's as you can see, it was well appreciated by math community, that indeed the CAC conjecture is true, and it's all irreducible modules are indeed the highest weight, lowest weight, or modules of intermediate series. Fine. So, as the case of these modules are settled, so people are again actually, as looking into the perspective of finite dimensional simple theory, tried to do the map Virasoro algebra thing. Okay, so they just defined map Virasoro algebra and see the pursue whether it has life for this representation theory. So again, so when you define Vir, you consider its positive, negative, and zero weight spaces as you done for a Vir. And now consider as analogous of Vir, you define the Verma module, actually the so-called Verma module. When you induce, you consider one-dimensional representation of Vir V naught and Vir V plus, where Vir V plus act trivially on that and Vir naught actually act as a C phi. The psi is nothing but that functional defined form Vir V 0 to C, and you induce it to the whole your U of Vir V. Unlike the Vir case here, you need to worry about the finite dimensionality of weight spaces, and there are results for it. And some by standards, some of the, like standard representation theory, one can prove that V psi is the unique irreducible. There exists a maximal submodule for M psi, and the quotient is a unique irreducible module. For B, CT tau inverse, the Keming Lau studied these modules for especially this Lorentz polynomial ring in one variable. They proved that any V is a irreducible Harish-Chandra module, then V is a uniformly bounded single weight module or highest weight or lowest weight module. The analogous result of Matthews. And moreover, we said they proved that if V is a highest weight module, then it is a tensor product of finitely many irreducible single point generalized evaluation modules. Okay. So note that. So this is not a single point evaluation module, unlike the, it would not come, unlike for uniformly bounded case, but for highest weight case, it is a product of finitely many irreducible single point generalized module. As it was done for CTT inverse. So quickly, Alistair Savage saw that it could be generalized for arbitrary finite dimensional associative Lie algebra, associative unital algebra, and he proved exactly the same result without any difficulties. Okay. So as this was settled, the more things actually for the Witt algebra, but the Witt algebra, the challenge was different. Even the modules for Witt algebra is not known. The classification problem was open. To show it more precisely, let me give you the definition of Witt algebras. So Witt algebra and its representation. So what are the Witt algebras? As for its n analog of torus. So n analog of circle. So you just take a polynomial vector, polynomial functions restricted to the torus, and it's just vector fields of all n-dimensional torus. Okay, so this is exact n-dimensional analog of Witt algebra of n equal to 1. Okay. And so consider an, it's a Lorentz polynomial ring. What is a Witt algebra? It's just nothing but it's all the derivations. Wn is nothing but the set of all derivations. So one highly anticipated, as for W1, there is a non-trivial central extension. Does there exist a non-trivial central extension for Wn case also? But unfortunately, it's not true. it's a centrally closed. For n greater than 2, Wn is indeed a centrally closed. What is the Wn? Wn is a derivations of n. You can have these Tm, Dis as their C basis, and they have a nice closed form of their bracket operations. Okay. So as we have defined Wn, let us make some noise about their representation. So what do you see about their representations? So for representation, Larson and Shen defined the tensor field modules. So T, mu, U, gamma, where U is a finite dimensional irreducible GLNC module. And gamma is an fixed member of Cn. And you define this action, the displayed action, where the EJIs are the elements of the GL. These things, a GLNC matrix. Okay. So this has a Wn module structure. Okay. If you notice, it is a uniformly bounded. It comes in a uniformly bounded category. Are they irreducible? Or what is their structure? So more precisely, if you know the GLNC representation theory, one quickly realize that. So if you take a standard representation, it means that Cn, the n-dimensional complex vector space, and takes its exterior powers, they form a they form an irreducible representation for GLNC for K0, 1, n. And if you take in the T, U, gamma, you replace gamma by these exterior powers, you would see that they're geometrically very nice, as they indeed form a DRAM complex. Okay, so they have these nice differential maps, which is a Wn module map, but be aware that it is not an An module map, it's a Wn module map where An these things. So this gives that this gamma k omega k gamma is reducible for k is equal to 1 to n minus 1, and this 0th and nth space they are irreducible if and only if gamma is in Zn. Okay, so we have these modules. So the first person to study these modules was Eswara Rao, who in 1996 kind of in one way result, one should say, that showed that these modules are most often irreducible modules. Okay, except you forget it about the differential forms, these DRAM complex. Okay, and the only liability is these simple modules, and he studied those modules also, and precisely said that the modules which gamma and these things are simple when gamma is not in Zn, and has a trivial one-dimensional simple quotient when gamma is in Zn. Okay, so that kind of initiated the theory initiated life in the problem of representation theory of Witt algebra. Now, as we are, all these things are uniformly bounded modules. So you should make some argument about the non-uniformly bounded module. So here, as we have no natural choice, we stick with the choice of Dn and for a Z grading, and we consider its eigenvalues. And so if you consider the Dn's eigenvalues, then you will have a nice triangular decomposition, which its 0th part is nothing but the dir, the n minus 1 analog of dir direct sum. Some you can analogous with the n minus 1 lower end polynomial. And then you analogously define it's you take an x to be an irreducible module for Wn naught and consider it's a generalized Worma module. Okay. And you will see that Lx has unique irreducible equation, but unlike these things we think, it will be Harish-Chandra if and only if, if X is a uniformly bounded Wn0 module. So note that it's a uniformly bounded module plays a crucial role in defining the Harish-Chandra modules, which are non-uniformly bounded. So unless for highest weight case actually. Okay, so please, and it's a very important thing that one should realize that it's actually it is induced from the uniformly bounded module. Okay, so it's a crucial fact here. Yeah, and so again, Rao actually made another attempt as he realized that the zero space is just nothing but Wn tensor, some Laurent polynomial ring. He considered the Wn semi-direct product An and assumed that the action is associative. What mean by action of associative? If Tn of V is nothing but Tm plus n of V. And one more condition that T0 acts non-trivial. Okay. So then he showed that the module has to have a tensor field module where V is a irreducible GL module and beta belongs to C. So that's a very important result in this part. And he became like more and more confident about that these are the only module. Either these things, either these highest weight modules or these tensor field module. So it prompted him to conjecture in 2004 that any non-trivial irreducible Harish-Chandra module over Witt algebra is a highest weight module of more tensor field or the tensor field or their quotient. So as this was an important conjecture, many mathematicians, including Vladimir Mozarchuk, Kemin Zhao, actually started their journey, but it was a very tough problem, given the only problem they faced actually in this thing that the uniformly bounded case. Actually. So it was, but here comes a very, very important inroad in that problem where they found out that if you have a non-trivial irreducible Harish-Chandra Wn module, their support, they made some comment about made some discovery about what would be the support. So V is a dense and uniformly bounded. What mean by dense? Dense means that its weight support of V is nothing but lambda plus Zn. Lambda plus translates of Zn. Okay, so that is the means by dense. And punctured means only zero is the liability. It means that support is Zn minus the zero. And we otherwise, if these two conditions are not, and then otherwise, then this is not the case, then V is the highest weight module. You will realize that highest weight module completely one lattice is off of the whole Zn weight, whole weight space. Okay. So this was a very, very important result. Okay. Then again, sorry. So then again, Gao has considered these WNAN modules and weight modules. And moreover, if V is uniformly bounded, this is very crucial. If T0 would act as identity, then automatically AN is a force to act associatively on V. Okay, this is a very crucial tensor field module. And if T0 acts 0, then whole your AN acts trivially. Okay, and so this was a very crucial result in this. I'm sorry. Am I audible? Am I audible? Yeah, some problem is there, internet issue there on my side.
Yeah, but we can hear you now.
Huh? Sorry?
We can hear you now.
Okay.
Cover the next. Yep.
Okay. Yeah.
Yep. We, we lost the speaker.
Yes.
Audible?
Yes. Yes.
I'm
Perfect.
very sorry for inconvenience. It's a connection stable is internet.
Yeah.
Somebody say that I'm audible?
Again.
I'm
Yep.
audible?
Yep.
Okay, so uh so this, yeah, so after they proved that the injecture is indeed correct, the conjecture is correct, and these are the things. The main problem here was the uniformly bounded case, where the crucial, what was the key innovation there is, invention is there is that AN cover, the so-called AN cover, which was crucial to kind of prove that the only uniformly bounded modules are only with the tens and with the support whatever given by Mosul, Chuk and Jar. Okay. And so as this has it has finished. So one considers the map Witt algebras. Just you kind of studies those functions from those modules to B, and so our aim is to in these things. So our work is related to the simple classification of Harish-Chandra modules for W and B or W and tensor B. But if on first hand you just can't solve that problem unless we take a finitely many copies of AN. So we take a finite dimensional abelian Lie algebras, and we consider this extended Witt algebras, where you will have this bracket operation. Yeah. And so aim is to study the Harish-Chandra modules for those things. And so you consider the tensor B, whatever you have extended Witt algebra, you tensor B, and you define the bracket operation. Okay. And so here the Cartan algebra plays, the role of Cartan algebra plays the DIs and on central C. Okay. Main result. What's the main result is that, so if you have finite is a Harish-Chandra weight module, then it will be either uniformly bounded or highest weight module. But further, as we expected, uniformly bounded has to be have single point evaluation module. The surprising result is the highest weight module also turns out to be a single point evaluation module. This is a very contrasting case from n equal to 1. Okay, so this is what our main result is. So just briefly, I will explain the steps of what I and or WNB. Okay, you just reduce it to that. One can do it using Keming's work and other mathematicians' work. And then classification of the WN tensor B is solved by Chakraborty and Rao in their paper, not like a recent paper, which helps us. And for WNB, the technique of AN cover by Futorni and Billig helps us to complete the classification. These three steps are very important. But finally, we are not done until the non-uniformly bounded case, actually. So the classification problem of non-uniformly bounded module actually hinges on the classification of irreducible uniformly bounded modules. Okay. So more precisely, this a very key result plays a role in classifying the all non-uniformly bounded modules, where the support of W plays a very crucial role. As shown here, it always actually important that whether 0 is there in the support or 0 is not there in the support. Okay, which is very crucial. And this of the non-uniformly bounded case. Okay. Yeah. So that's what I wanted to say. And I just thank you very much for all your patience. And again, apologies for the interruptions.
Well, thank you very much. Well, just imagine that we had all of us coming to Kanpur. The flight was more troublesome than these minor technical points. So, are there any questions? Can you say a word on this final step, the reduction from the product by AN to the algebra itself?
Very good
Previous
question.
slide.
Yeah. So what you would be able to prove is that the codimensional, see, S is a finite dimensional Lie algebra, so abelian things. So you will find you will able to prove using the results of K-Min Zhao and all that it is immaterial. They are you can go, you can literally have one copy of AN, actually. The other copy is redundant. So you will need the theory of Heisenberg-Virasoro algebra here. Okay, so it's I hope you kind of that's in case kind of yeah.
Any other questions? So if not, thank you very much for a very interesting presentation, and see you all next week.
Yeah,
Thank you.
Thank you again. Thank you for the opportunity.